Hello guys, welcome back to my YouTube channel. And in this video, I would like to do something special that introduces a special function. So let's get started as always. So you could have guessed it that special something is actually an integral. I love integrals, don't I? So anyways, let's call it I. This is defined as the integral from negative infinity to positive infinity of e to the negative x squared times 5x squared plus 2 times x to the fourth divided by x squared times x squared plus 1 dx. And before saying any much about this integral, notice that we have a factor of x squared in the numerator and a separate x squared in the denominator. So let's cancel them out. So we have the integral from negative infinity to positive infinity of e raised to negative x squared times 5 plus 2x squared divided by x squared plus 1 dx. We just removed the factor of x squared from the numerator. And notice another fact, that this integrand is an even function. That means even over the negative region. So basically this integral can be split as integral from negative infinity to 0 of e raised to negative x squared times 5 plus 2x squared divided by x squared plus 1 dx plus integral from 0 to infinity of e raised to minus x squared times 5 plus 2x squared divided by x squared plus 1 dx. And looking at this first integral, I would like to do a quick substitution. Say y equals negative x. So we have integral now from, this is just going to be infinity and this is going to be 0 of e raised to negative y squared times 5 plus 2y squared divided by y squared plus 1, because y is negative x and x is negative y, so negative y squared is again going to be positive, and dx is negative dy plus this other integral is unchanged, e raised to minus x squared and 5 plus 2x squared divided by x squared plus 1 dx. So notice that we can use this negative to flip the upper and lower bounds. So we have integral from 0 to infinity, and now keeping the upper and lower bounds the same and also the form of the integrand, we can just change this variable y for any other variable wx, because it doesn't matter what variable we have as long as um, the integrand and the upper and lower bounds remain the same in a definite integral. So instead of y, I can again use x. So we have 5 plus 2x squared divided by x squared plus 1 dx plus integral from 0 to infinity of e raised to minus x squared 5 plus 2x squared divided by x squared plus 1 dx. And what was all this equal to? Just our regular integral I, right? So I can just be written as 2 times the integral from 0 to infinity, adding both of these up, e raised to negative x squared times 5 plus 2x squared divided by x squared plus 1 dx. Fair enough. Now I would like to actually rewrite this thing as integral from 0 to infinity of e raised to minus x squared times 2x squared, and then I want to write 5 as 2 plus 3 divided by x squared plus 1 dx. And you'll see in a minute why, because now I want to split these integrals as 2 times integral from 0 to infinity of e raised to minus x squared times 2x plus 2 divide 2x squared plus 2 divided by x squared plus 1 dx plus this 3 and this 2 will make us 6 times the integral from 0 to infinity of e raised to negative x squared times we have a 1 over x squared plus 1 dx. Nothing in the numerator now. So notice that we can actually cancel out the denominator because the numerator is just twice the denominator. So we can pull that 2 out. So we have 4 times integral from 0 to infinity of e raised to minus x squared plus 1 divided by x squared plus 1 dx plus integral 6 times integral from 0 to infinity of e raised to negative x squared divided by x squared plus 1 dx. Notice that these cancel out nicely, so we just have 4 times integral from 0 to infinity of e raised to negative x squared dx plus 6 times integral from 0 to infinity of e raised to negative x squared divided by x squared plus 1 dx. I'm going to write the second integral as it is for now because notice that the first integral is just the Gaussian integral, which is going to be square root of pi over 2, this dividing by 2 because it's an integral from 0 to infinity, not minus infinity to infinity, in which case we would have obtained the square root of pi. And I would like to call this integral I1. We have 6 times I1, that is equal to I is equal to 4 times square root of pi over 2. So let's just simplify that a bit. So we have 2 times square root of pi plus 6 times I1, and I would like to do I1 on a fresh page. See you there. So we have our I1 equal to integral from 0 to infinity of e raised to negative x squared divided by x squared plus 1 dx. And since we have a denominator like this, a good alternative would be to to use Leibniz technique or Leibniz rule or Feynman technique. So if we use Feynman technique, so we have to parameterize this, say I1 of t is equal to integral from 0 to infinity of e raised to negative x squared times e raised to negative t times x squared plus 1 divided by x squared plus 1, and we've parameterized in such a way that we cancel out the denominator on taking the partial derivative because that's the motivation of using this parameterization in for this integral at least. If we had a log, then we would have just taken the parameter inside the log like yesterday's integral. So now taking the partial derivative, so we have I1 prime of t is equal to integral from 0 to infinity of e raised to minus x squared divided by x squared plus 1 times the partial derivative with respect to t of e raised to negative t times x squared plus 1 dx. This is just going to become negative integral from 0 to infinity of e raised to minus x squared divided by x squared plus 1, and we have x squared plus 1 down by chain rule, and e raised to negative t times x squared plus 1 dx. Now notice the great part of using this parameterization was the denominators cancel, so we just have negative integral from 0 to infinity of e raised to negative x squared, and we can write this as e raised to negative tx squared times e raised to negative t dx. We can pull the e raised to negative t out because it does not depend on x. We have the integral from 0 to infinity of e raised to negative x squared times t plus 1 dx. And look at this is a general form of the Gaussian integral. So this is just going to be minus e raised to minus t times square root of pi over 2 times the square root of whatever quantity was multiplied with this x squared, so t plus 1 in this case. Fair enough, that's I1 prime of t. Now we actually need to get back our I1 of t and then plug in suitable upper and lower bounds to get I1 finally. So I've written down the expression for I1, the and its parameterized form I1 of t and I1 prime of t that we simplified earlier. So now we want to find upper and lower bounds, suitable upper and lower bounds, such that when you integrate I prime of t dt from those upper and lower bounds, you end up with just your regular I1. So let's first try to evaluate what those upper and lower bounds are going to be. So notice that as t tends to infinity, I1 of t goes to 0 because this e raised to negative t will make the whole thing decay as t tends to infinity. So one of our bounds is going to be infinity. And how can you relate I1 and I1 of t? So notice that when t is equal to 0, that's when we have e raised to 0 here and this thing goes to 1. E raised to 0 is 1. That's when I1 of t is just equal to I1. So our lower bound should be 0. Because by the fundamental theorem of calculus then we'll have the limit as t goes to infinity of I of t minus I of t equals 0, which is just going to be, this thing will go to 0, negative I1. This is I1 of t and I1 of t equals 0. So negative I1, and notice that this negative and this negative are basically going to cancel out. So let's cancel them out right away. So I1 is basically integral from 0 to infinity. Rather, negative I1 is integral from 0 to infinity of I prime of t dt. But we know that, right? And assuming that the negatives cancelled out, I1 is just going to be integral from 0 to infinity of I prime of t. We know I prime of t. Let's just plug that in now. E raised to minus t times square root of pi divided by 2 times square root of t plus 1 dt. It's an integral with respect to t. So let's pull out the constant. So square root of pi over 2 is a constant here. And we have the integral from 0 to infinity of e raised to negative t divided by square root of t plus 1 dt. And might I suggest a substitution? Let w squared equals t plus 1. So we have square root of pi over 2 times, well, when t equals 0, t plus 1 or 0 plus 1, w square is going to be 1. And when t tends to infinity, even w tends to infinity. So we've integral from 1 to infinity of, now instead of this negative t basically, negative t is basically going to be 1 minus w squared. So minus w squared plus 1 on top divided by square root of t plus 1 is just a normal w, and 2w dw is basically dt. So dt is 2 times w dw. Now the best part is the w's will cancel out nicely. The 2's will go away. So we just have square root of pi times integral from 1 to infinity of e raised to negative w squared, and plus 1 is just multiplying by e raised to 1, which is e dw, and we can plug the e out too. So e times square root of pi times integral from 1 to infinity of e raised to negative w squared dw. But notice that since we don't have a 0 for the lower bound, this is not going to be the Gaussian integral. But don't worry, mathematicians found a great way to deal with stuff like this. Let me just explain this on a fresh page. So remember that our Gaussian integral was the integral from 0 to infinity of e raised to negative x squared dx. But in the cases where we don't have exactly upper limit as infinity, say we have upper limit as some x, then we have to change the inner variables to say e raised to minus y squared dy. Then, but what's the value of the Gaussian integral? First, let me tell you that is going to be square root of pi over 2, right? I made a bunch of videos on this. So say if we have something like this and you multiply by the reciprocal of this, so you multiply by 2 divided by square root of pi. This is what mathematicians called the error function, the Gaussian error function. So it's basically your normalized Gaussian integral, normalized generalization of the Gaussian integral. Why do I say normalized exactly? That's because if you let x tend to infinity, so you have the error function of x as x tends to infinity, this is just going to be 2 over square root of pi times integral from 0 to infinity of e raised to minus y squared dy, and this is the Gaussian integral. So we have 2 over square root of pi times square root of pi over 2, and we get 1. That's why it's normalized. So for a regular limit upper bound of infinity, this will just become 1, unlike the normal Gaussian integral square root of pi over 2. So this is the error function, is basically the normalized generalization of the Gaussian integral. But what if we, like our case, we had a lower bound of 1 and upper bound of infinity? So in that case, let's extend this out. So integral from 0 to infinity well, let's take a certain value x, like the generalized version of it. So say you have integral from 0 to x of, say, yeah, e raised to minus y squared dy plus integral from that x to infinity of e raised to minus y squared dy, and this by linearity of integrals is just integral from 0 to infinity of e raised to minus y squared dy. This is going to be square root of pi over 2. This is almost the Gaussian integral, but this is square root of pi over 2 times the Gaussian error function. We just defined that on top. Plus this is some other function, I don't know, let's just call it r of x. So r of x is just going to be why don't we factorize by this? So we just have 1 minus error function of x, and we're dividing by that, right? So we have 2 divided by square root of pi, and this entire thing is what we call the complementary Gaussian error function, which is defined as 1 minus the Gaussian error function. So formally, this is just going to be 2 over square root of pi. This is the normalization factor, just like we had for the Gaussian error function, times integral from x to a certain infinity of e raised to negative y squared dy. That's your uh, Gaussian complementary error function. But notice that in our case, in our original integral that we had to calculate, we had integral from 1 to infinity of e raised to minus x squared dx, for example. I think it was w. Well, this is just going to be taking this normalization factor on that side, square root of pi over 2 times the complementary Gaussian error function of 1, because the lower bound is 1 and x, the parameter was basically the lower bound. Well, that's exactly what our integral now converts to. So I1 now is just going to be this square root of pi times e times square root of pi over 2 times the complementary error function of 1. So simplifying this will just give us e times pi over 2 times the complementary error function of 1. Fair enough, that's I1 now. And we know I1, we know our initial part. Let's just plug it back to get an expression for I. So having known everything, we know the general equation too. So I is nothing but 2 times square root of pi plus 6 times I1. We know I1, so this is just going to be 2 times square root of pi plus 6 times pi over 2 times e times the complementary error function of 1, and then cancelling out common factors, we just end up with 2 times square root of pi plus 3 pi e times the Gaussian complementary error function of 1, which I don't know, if you want to write this as 2 times square root of pi plus 3 times pi e times 1 minus Gaussian error function of 1, you can do that also. And what was I though? I was just integral from negative infinity to infinity of e raised to minus x squared times 5x squared plus 2x to the fourth divided by x squared times x squared plus 1 dx. So we basically used a Feynman technique or Leibniz rule to simplify this integral, and then we got this nice answer. This answer is pretty special because it necessarily does not have a numeric value when after we introduce this Gaussian error function, complementary error function and error function. It doesn't have an exact numerical, a closed form beyond this in terms of any other known constants apart from the pi's and the e's that we got. I mean, that's why this question is pretty uh, exciting to, if when we look to introduce these special functions. And there are many integrals that introduce these special functions. So I hope you enjoyed this. That's all for today. So guys, please like, share and subscribe to my channel. I need to grow. I need more followers. I need more subscribers. I need more views and likes per video, because that will encourage me to make more videos with uh, more interesting content in the future. But you can follow me on Instagram too. I have the username gamma_digamma. So check out my Instagram page. In the meantime, stay home, stay safe, have a great day, and peace out.